Hello everyone, welcome to week 2 live session of NPTEL Semiconductor Device Modeling and Simulation course. I am Om Maheshwari and today we will solve some questions that may help you in your assignments as well as in your exams. So let us start. So in this week we will learn about reciprocal space, doping, band structure and effective mass. So let's learn that through the questions. I hope you all have seen the videos for this week. So start with some very simple theoretical questions. First question is, when a small amount, say a few parts per million, of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased manifold. Such materials are known as A. Extrinsic semiconductors, second intrinsic, third elemental, and fourth compound. Right. It is known as extrinsic semiconductors. So, so what we essentially do to make a semiconductor usable. So generally, for most part of this course, silicon will be our point of interest as a semiconductor material. So what silicon has is it has valency of 4, right? So it forms bonds with 4 other silicon atoms to make the entire crystal. But in its inherent state, silicon has a very low conductivity. So to we modulate its conductivity uh, and we so that it has more number of free electrons or holes to conduct. So to do that, we do something known as doping. So currently we have the intrinsic silicon. We dope it with some, uh, sorry, just a minute. Okay, sorry for the disturbance. So, okay, so we were discussing intrinsic semiconductors and doping. So, in the intrinsic semiconductor, to modulate its properties, we introduce some additional materials, uh, which is basically that process called doping. And doping makes the semiconductor into a extrinsic semiconductor. So, basically, that's what it is written here. The impurities are added to the pure semiconductor, which is the intrinsic semiconductor, to modulate its conductivity. or increase its conductivity. Such materials are known as extrinsic semiconductors. Okay, so let's see the next one then. A silicon crystal doped with Nd 10 to the power 13 donor atoms per centimeter cube. Given that the intrinsic carrier concentration is 10 to the power 10 per centimeter cube, then what could be the electron and hole concentration, assuming complete impurity ionization? So, can you guys attempt it? Then we will solve it. Does anyone know how to do this question? Are you able to solve it? Okay, so let's see how to solve this one. So we have a silicon crystal. It is doped with some donors Nd, Nd equal to 10 to the power 13 per centimeter cube. The intrinsic carrier concentration is Ni. Ni is 10 to the power 10 per centimeter cube. So Ni is basically the number of electrons or holes that are generated without any doping due to just the thermal uh, recombination and generation. Nd are the externally doped uh, atoms that generate electrons. Okay, if so, the question is if there is what could be the electron and hole concentration assuming complete impurity ionization. So directly we can say that the number of electrons n would be equal to Nd, and when n equal to Nd is 10 to the power 13 per centimeter cube, the holes with P would be Ni square by n, which is equal to 10 to the power 10 square by 10 to the power 13, which is 10 to the power 20, 10 to the power 13, which is 10 to the power 7 per centimeter cube. So the electron concentration is 10 to the power 13 and the hole concentration is 10 to the power 7, which is option B, as mentioned by Brijmohan. Okay, so let's see the next one.
It, it is YZ.
Okay, so the question is which of the following materials are used for making lasers? So for for lasers, we need what is a laser? When we give some electrical impulse to the laser, it generates photons, right? So basically, if we have an uh, let's say this is valence band and conduction band. If some electron is there in the conduction band, when it comes back to the valence band, the energy, it will lose some energy, right? Equal to band gap, right? So when it loses energy, if this energy is lost in form of photons, which are characterized by h nu, then we can say that some light energy is being produced when the energy when the uh, some light energy is being produced when the electrons de-excite from the in the semiconductor. But not all semiconductors can do that. Not all semiconductors can produce uh, the 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 light when they lose energy, when the electrons lose energy. Some produce heat, and silicon is such example. So only direct band gap semiconductors can radiate energy in form of some light energy. And direct band gap semiconductors are therefore used for making both the lasers as well as LEDs also. So both for what is LED? LED is light emitting diode. They are also a form of semiconductor, right? Diodes are made using semiconductor. Diodes are just PN junctions made using some semiconductor. So those are also made using direct band gap semiconductors. So what is direct and indirect band gap is simply, let's take an example of gallium arsenide. So the minima of the conduction band and the maxima of the valence band is, let's say, EV, this is EC, and this is EK diagram, right? Both have the same momentum. This is a direct band semiconductor. Whereas in indirect band gap semiconductor, what happens is the EC minima and the EV maxima are not at the same momentum level. So they transition to some intermediate state and then come to here. So that makes it an indirect band gap semiconductor. Whereas an electron, if it has to come from here, it can directly go to here. So this is radiative, and this is non-radiative for indirect band gap. So that's why answer is option A, direct band gap semiconductors. Okay, so let's take the next one. Please see this question and we'll solve it. Yeah. So let's see how to do that. Okay. So okay, we have here wavelength lambda is given as 0.061 nanometers, which is in 10 to the power minus 9 meters. Okay. And lattice constant A is 0.3 nanometer. The plane of our concern is 110, and the order of diffraction n is 2. The Bragg's law is 2d sine theta is n lambda. Okay, so and d, we have something we do not know right now. So d is just a by h square plus k square plus l square. That is just the interatomic distance between the planes in 110. So it would be okay. So let's put everything in the place. 2 into a is okay. Let's just put it in nanometer terms for now. 0.3 upon under root 1 square plus 1 square plus 0 square sine theta equals to 2 times 0.061 nanometer. So both are nanometers, so I can cancel on both the ends. So 2 into zero point 0.3 by root 2 is 2 times 0.061. Okay, I fixed sine theta. So sine theta equals to root 2 into 0.061 upon 0.3. So what is its value? It is 0.28755 sine theta. Theta is sine inverse 0.28755, and it is around 16.711 degrees. So answer is option D. So I hope this one is clear. Let's see the next question now. Given the EK diagram, which of the following has the highest effective mass? Okay, so let's see this. Okay, so where do these EK diagrams come from, right? They come uh, from the solutions of Schrodinger equation. Okay, so basically, so I don't know if you know how to solve the Schrodinger equation. Um, so let me show you some basic. So what Schrodinger equation is del 2 psi by del x square plus 2m by h cross square e minus p psi equals to 0. So this is a simple one-dimensional Schrodinger equation, and basically the solution of the Schrodinger equation gives us for a particular, let's say, so what we have, right, in a semiconductor, what we have is different atoms spaced with some spacing apart. Okay, so if we solve the Schrodinger equation for these atoms, we know we calculate the potentials and their energies in the space. What we can find out is how their energy bands would look like. Okay, so here are just some examples, let's say, of some hypothetical materials for which the energy with respect to this k is you can say is the momentum here. So with respect to momentum, how the uh, energy looks like. So the solution that we get, let's say, for a simple constant potential uh, problem, let's say if V is simply V naught, then the solution of the Schrodinger equation is in terms of psi equals to let's say A sine kx, and k is nothing but under root 2m by h cross square E minus V0. So this is a simple solution of the Schrodinger equation. And basically here we have just plotted E versus K. So if we let's say if we look at this, so we look at this part, um, it gives us relation between E, K and M. Okay, so I can see let K square equals to 2m by h cross square E minus V. So, or if we write it in form of a differential equation, it will be 1 by m star to 1 by h cross square del 2 E by del K square. So, what we see from here also, if m is our concern, m is um, k square upon E minus V h cross square. Okay, so this is actually not correct. Just I have made a very crude approximation here, but we can see M is M will be large if energy is lower and K is higher. Okay, so for let's say for same value of K, if E is higher, then your M will be lower. So basically what this is telling us is the curvature. Okay, so so higher the curvature, lesser is the effective mass, or flatter EK will have higher effective mass. So among these options, which has the highest effective mass, it would be option D, right? This is the flattest. So there is minimum curvature here, so it will have the highest effective mass. Okay, so what I told, all this is very like uh, inside where we get this EK from and what is the relation of M. But I suggest you do not, like, you actually see the solution of the Schrodinger equation, and it would be very easy to follow from there. It is I've just shown a very basic overview of that. You can see from here also we had this, right? K equals to under root 2 m by straw square E minus V. So K square equals to 2m upon h cross square E minus V. So E minus V equals to h cross square K square by 2m. So if I take the derivative, del E by del K equals to h cross square 2k by 2m. So 2 and 2 will cancel. I will get h cross square k by m. Or if I take another derivative of this, del 2e by del k square will be h cross square upon m, right? So your m is simply, or okay, if I send h cross to the right hand side, 1 by m equals to 1 by h cross square del 2e by del k square. So this is from where we get this relation that you generally see in books. So this is the curvature. So higher the curvature of the EK plot, lower will be your effective mass. Does this make sense? Is there any doubt in this? Or have you guys seen the solution of Schrodinger equation or not? Okay, so I'm assuming there's no doubt in this, then I'll move ahead. Fine. So based on the previous questions insights, can you answer this one? Right. So you see the curvature in this A1 is much higher, right? Steeper compared to B. So the effective mass here was lower. Effective mass is this is curvature. It is inversely proportional to your curvature. So your answer is option B. The effective mass of particle A is less than effective mass of particle B. Okay. All right. So let's see the next one. Which of the following can be a wave function? Yeah, we just saw that in the example, but can you tell me why others cannot be a wave function? Okay. Mhm. So there are, let's say, four properties of a wave function that it must follow. First one is a wave function, I'll call it psi. Psi must be continuous. Second one is psi must be finite. Third one is psi must be single valued. The fourth one is minus infinity to infinity psi star, which is what you said, must be equal to 1. Probability must be 1. Now if you look at the graph of sin x or cos x or any sinusoidal function, it is continuous. Its values are finite between 1 and minus 1. It is single valued. Single valued means at edge at each x it has a single y, single valued. And if we do its normalization, this is the normalization condition, it would give us 1. So we'll see that one later. But if we see the graph of, let's say, tan x, so tan x looks something like this, right? This is tan x, or what else is there? Cot x. Cot x is also something like this. and we have sec x. Sec x is something like this. Okay, so the problem with all of these is simply we can directly see is it is not even continuous, and the wave function must be uh, continuous as well as differentiable. So that property needs to be satisfied, and that can only be satisfied among these options by a sinusoidal or even a cos function. Right? This is just a shifted sign. So answer is option C here. Okay, so let's see next question. Okay. Uh, so the question is for a particle in a 1D infinite potential well, its wave function is psi x equals to a sine kx, where k equal to n pi by l. Calculate a. Okay, so we can easily do this. So to do this, what we just have to do is do the normalization condition, that is minus infinity to infinity psi square x dx is 1. So we have into infinity a square sine square kx dx equals to 1. So can you solve it further? Replace sine square x by its identity to convert it into cos theta. Yeah, yeah, definitely. For 1D dimension, if the potential value is between 0 to A, 0 to L, which is the case here, minus infinity to infinity would change to 0 to L. Right. So what you can do here is convert this sign to, let's take A square outside, integration 0 to L, 1 by 2, 1 minus cos 2 kx dx is equal to 1. Okay. And k is n pi by L. Let me divide by n pi by L. Okay. And 1 to A square, half we can take outside only. It is x minus sine 2 n pi by, okay, x will be not x by L. 2, there's no need of 2, then if it's n pi x by L, yeah.
I just wanted some help here.
I'm in a meeting, can I? Yeah. Sorry for that. You were saying something, sorry. Yeah, 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 yeah. Okay, yeah, that is essentially what we're doing here also. So that would be okay. We can directly take this. Then we just put it in the limits between 0 and 1. And what you would find that this term would vanish. Right? That's what you might have been getting. So here from here you will get that. Uh, it was 0 to L, sorry. From here you must be getting that L uh, L term, right? Yeah. So basically what you would have gotten is 1 equals to A square L by 2. So A is root 2 by L, right? Which is option A. Okay, so that's one thing, but do you guys know where are we getting this A sine kx from? Yeah, for the infinite well problem, it is the solution of the Schrodinger equation. So that's a pretty standard solution, and I think you can easily find it on internet anywhere. I'm not sure if that was in the video this week. But I hope that's easy to follow. What we are talking about here makes sense. Okay, so see the next question. In an n-type doped semiconductor, the Fermi level is closer to conduction band edge, closer to valence band edge, exactly at the middle of the band gap and within the band gap. Okay, right, for an n-doped semiconductor. So what Fermi level tells you is the it can tell you what kind of semiconductor you have. Is it in an n-type semiconductor or a p-type semiconductor? Um, so for an n-type semiconductor, what we have is EC, EV, EI, and EF is somewhere around here between EI and EC or closer to EC. So this EF minus EI distance is actually that gives us or EF minus EC distance directly gives us n equals to NC e to the power EC minus EF by KT. This will directly give us how many electrons are there in this semiconductor. And the closer we are to EC, that means the more electrons we have in the semiconductor. So for an n doped, when we dope it with n-type impurity, the n is closer to Nd, right? The number of electrons is donated by those pentavalent impurity atoms is each atom will give one electron, and in n-type dose semiconductor, the number of electrons would then directly become equal to the dopant concentration. So that would shift your Fermi level closer to EC. And similarly, in a p-type semiconductor, if the semiconductor is p-type, so EI signifies the intrinsic line, right? If EF is at EI, that means your symmetry and intrinsic. If EF is below EI, that is closer to EV, that means it is a P-type semiconductor. So there was an answer in the chat. Yeah. So that's very simple question. Closer to the conduction band edge, we have for an N-type semiconductor. Okay. Identify the correct statements about the silicon crystal from the below figure. Okay. So this is a very good question. So there's something more it has introduced us something new as E impurity, right? We only talked about Fermi level and intrinsic level or EC or EV till now. There's something as E impurity. So what E impurity is, so I can directly see, okay, it's near EV, it must have to do something with P type, right? So E impurity basically is, so in a P type semiconductor, what would happen is what you have is acceptor atoms, right? So those acceptor when in a silicon crystal, when you dope with uh, p-type dopants, could be boron or uh, any other group 3 elements. So what would happen is their energies would lie, those atoms would lie somewhere here in this impurity level. And as you know, those these are acceptors, right? These can accept electrons. So what would happen is the electrons from the valence band would go to this impurity level and leave behind a hole. That's how your p-type semiconductor is made. The impurities, the electrons from this valence band, they go to to this acceptor level and leave behind holes. And these holes are what then are the majority carriers in a p-type semiconductor. So this is the question here. Similarly, if we do the same thing for the n-type, which is the next question here. So in n-type, what happens is the impurity is it is phosphorus or arsenic, or which are group 5 elements, right? So they have one additional atom. So silicon has 4 valency, they have 5. They have one additional atom, so they can donate one electron. So what they do is these pentavalent atoms, they donate one electron into the conduction band. They ionize here from here and donate one electron to the conduction band. So that's how we get electrons in the conduction band for the n-type semiconductor. So the answer for this one would be silicon doped with pentavalent impurity n-type. Okay, so let me give a few more questions. Just a minute. Okay, so let me write a question. Question is, in a semiconductor, the Fermi energy level lies inside the conduction band. Then what? Then the semiconductor is known as. Okay, I'll not give the options. Does anyone know the answer to this? So what they're saying is your this is EC, this is EV, your EF is here inside the Fermi level. Okay, so these are known as degenerate semiconductors. So what happens in degenerate semiconductors is like like we had some donor level here, right, which was giving electrons. But what you do is you dope it so much that this actually becomes the edge of your EC, and all these states are completely filled by electrons. So this effect is known as. So first, what happened is your band gap has been narrowed. Your band gap has reduced. So this effect is known as band gap narrowing, and those semiconductors in which it happens is are degenerate semiconductors. Like they're not semiconductors anymore. They behave like metals. All the electrons they have taken so many electrons from the donors that uh, their their states in EC below EF are completely filled. So these are known as degenerate semiconductors, where they have lost the property of the semiconductors and they have become almost metals. So this is probably something new. So let's take one more question. So in a semiconductor, you have electron density is 10 to the power 16 per centimeter cube. EC minus EF is 200 milli electron volts, and intrinsic carrier concentration Ni is 10 to the power 10 per centimeter cube. The question is for n equals to 10 uh, 0.5 into 10 to the power 16 per centimeter cube. What is EC minus EF? That's the question. Can you guys attempt this? It's a simple question. Okay, let's solve this. So we know that, right? N equals to NC EC minus EF by KT. Okay, so what you're given is 10 to the power 16 is NC e to the power 200 millielectron volt upon, so KT usually, okay, let me write it as KT for now. So 200 millielectron volt by KT is 10 to the power 16 or I can write here NC equals to 10 to the power 16 upon 200 millielectron volt by KT. Okay, now for your second case where your N is N2, let's say NC to the power EC minus EF by KT. So here N2 is 10, 0.5 into 10 to the power 16 NC EF by KT. So here we have to find EC minus EF by KT. EC minus EF by KT is ln 1.5 into 10 to the power 16 by NC, and which will be C minus EF by KT ln 1.5 into 10 to the power 16, and NC is this 10 to the power 16 into e to the power 200 by electron volt by KT. So if I take this in ln, this e to the power, this thing will come out. It will be F by KT ln 0.5 into 10 to the power 16 by 10 to the power 16 plus ln 200 MeV by KT EC minus EF by KT equals to 200 MeV by KT plus ln 0.5, just 7.5 only, I think. So this will cancel. So I can write EC minus EF equals to 200 MeV in plus KT ln 0.5, and KT is typically 26 millielectron volt. This is at room temperature. So 200 millielectron volt plus 26 millielectron volt, and ln 0.5 is uh, ln 0.5 is minus 0.693 and into 26 would give me 200 MeV minus 18.02 MeV. Okay, I made one mistake here. It is EF minus EC. This would also be negative one. So EC minus EF would become 200 MeV plus 18.02, which is 218 milli electron volts. Which is the answer. Okay, so please be mindful, this is the correct formula. I made a mistake earlier. It is EF minus EC. Is it clear? Do you want me to repeat it? Bridge move on. Did this solution make sense to you? Or is there any doubt here? Okay, so uh, let's end here today. Let's end early. Uh, I don't have any more questions. So if you have some questions, you can ask, else we can close the session for today. Okay, then. Uh, thank you everyone for joining. We will meet again next week. And if meanwhile, if you do get any questions, please feel free to email me throughout the week. Thank you.